The problem states a substance contains 64.9% carbon, 13.5% hydrogen, and 21.6% oxygen by mass. At 120 degrees Celsius and 750 millimeters of mercury, 1 liter of the gaseous compound weighs 2.30 grams. And the problem's asking what the molecular formula is. Well, if we're going to be looking at the molecular formula, we need to determine the empirical formula. The empirical formula is generated by looking at the percentages of each substance in the compound. In this case, we have 64.9% carbon, we have 13.5% hydrogen, and 21.6% oxygen. Everything's by mass, so we make the assumption that each percentage is actually a gram amount. So if we had 100 grams of the compound, we would have 64.9% carbon, or 64.9 grams carbon, 13.5 grams hydrogen, and 21.6 grams oxygen. Convert all of those to moles using our knowledge of empirical to molecular formula conversions. So to determine the empirical formula, we need to get mole equivalents, so we can compare mole ratios of each element in the substance. So to find the mole amount of carbon, we use the molar mass, 12 grams per 1 mole of carbon. We know that 1 mole of hydrogen has a mass of 1 gram, and we know that 1 mole of oxygen has a mass of 16 grams. Calculate our mole amounts, and we get 5.41 moles, 13.5 moles, and 1.35 moles. Now that we have everything represented in moles, we can look at mole ratios, and we take the smallest mole amount, divide all numbers by the smallest mole amount to find how many moles of each substance we have relative to the others. And we get 4 moles of carbon for every 10 moles of hydrogen for 1 mole of oxygen. So our empirical formula is equal to C4H10O. The problem's asking for the molecular formula of our gaseous substance. Knowing that we have a gaseous substance and we only have a temperature, a pressure, and a volume, we can determine the number of moles. So we're given a temperature of 120 degrees Celsius. Remember that when we're using any temperature in the gaseous state and we're using PV equals nRT, we have to have an absolute scale, so we can't go below 0. An absolute scale is Kelvin, so we add 273 to that to get our Kelvin temperature, so we would have 393 Kelvin. We have a pressure of 750 millimeters of mercury, and we also have a volume of 1 liter, 1.00 liters. So we'll add that in here to keep our sigma constant. If we're going to look at what we need to know, the empirical formula, the molecular formula, in the end, we are going to need to compare the molar mass of the molecular formula to the molar mass of the empirical formula. And that'll tell us if our empirical formula is the same as our molecular formula or how many multiples greater our molecular formula is from our empirical formula. Well, we can look up the molar mass of the empirical formula. We can just add the mass of carbon times 4, because we have 4 carbons, hydrogen, the mass 1 times 10, and we can take the mass of oxygen times 1, add all of that up, and we should get a total mass of 74 grams per mole. So we know the empirical formula, molar mass, is 74 grams per mole. Now, if we take the information given that we have grams per moles of molar mass, and we look at what we're given in the problem. We're given a temperature, a pressure, a volume. We're also given a mass of the substance. And if we're going to determine molar mass of the substance, we need to know grams, and we need to divide that by the number of moles. So we go back to our P equals nRT formula. We have enough information in this formula so we can solve for n, number of moles. So we can take n, rearrange the equation to solve for n. We would have a pressure, 750 millimeters mercury, a volume of 1 liter, a temperature, and R, we would end up looking up. In this case, we want to use the R value that is linked to having a pressure units of millimeters of mercury. Take all of our values, plug them in, and R you would look up and make sure you identify the correct R value to use. Because we're using millimeters of mercury, you're going to use the R value that's listed as the 62.4 liters per millimeters of mercury, or torr. Millimeters of mercury and torr, same thing. John Torrey was the guy who used the barometer and discovered the use that you can measure in millimeters of mercury. So he included his torr, last name, as part of the name. So millimeters of mercury and torr, the same number, just change the units. So 62.4, and the units on this would be liters per millimeter of mercury over a mole Kelvin. To save space, you would plug all of these numbers in, one for pressure, volume, R, and T, and you are going to get an N value, a number of moles, equivalent to 0.0306 moles. So that's how many moles we have per 1 liter of our substance. And what we want to do now is find the molar mass of our molecular formula, the molar mass of our substance. So to find the molar mass of our substance, we're going to divide the number of grams we have of our substance by the number of moles. So we take the 2.30 grams divided by the 0.0306 moles, and we get the molar mass of our actual substance, which is the molar mass of the molecular formula. And that's roughly equivalent to 75.2 grams per mole. Stepping back over to our molecular formula, molar mass to molar mass of our empirical formula, the comparison, we would say that our molar mass of our molecular formula is roughly 75.2 grams per mole. The molar mass of the empirical formula is 74. That's approximately 1. So that means that we would take our empirical formula, multiply it by 1, and after multiplying by 1, we would have the molecular formula mass, which doesn't actually change anything. It stays the same. If this was a multiple of 2, then we would take carbon, multiply it by 4 and get 8, or 2 and get 8. Take hydrogen, multiply it by 2 and get 10. Take oxygen, multiply it by 2 and get 1. So whatever the multiple is, you multiply the subscript for the number of atoms by that multiple. Being 1, it stays the same. Our molecular formula is the same as our empirical formula.